Welcome to Sorcerer's classes. In this video lecture, I'll be talking about some of the concepts that are involved in the physics syllabus of IIT JAM entrance exam, and essentially I'll be talking about some of the concepts that you need during the exam, which can help you out immensely when you're trying to guess the solution to a problem. And my recommendation is not to start solving the problem right away. Instead, what you do is you try to make educated guesses, and you try to basically find out or figure out any kind of way that makes the calculations very simple, or basically shorten the calculations, because you don't have a lot of time to spend on each problem. And if you end up spending a lot of time doing long calculations for one problem, it ends up basically taking away time to actually go through the other questions. So in this video, I'll be actually covering some concepts related to vector calculus. So when we talk about vector calculus, we talk about vector fields, and not just vector fields. Rather, I would say that in general, we can just say fields, because we can also have scalar fields. And fields. And so what does it mean by a field? So let's say that we have a quantity phi is a scalar quantity which just has value, and let's say it has a value which is different at different points in a region of space. So let's say this is a region of space, and phi has different value at different points. So this is a three-dimensional space, so there are three coordinates. It's better if I just draw it right away here. And so phi changes with each one. As you move from one point to another, phi changes accordingly. And this is a scalar field because there is only value that changes. It does not have any magnitude or direction. On the other hand, if you have a vector field, it has both value and magnitude, and it is going to look something like, so let's say I'm just randomly drawing arrows just to show that the vector. So it means that at each point the vector has a value, and the length of the arrow tells you what the value is, and the direction tells you which direction the vector is pointing. So when you have a well-defined function, and the fields are basically fields have continuous derivatives, we can talk about the concept of differentiation. Of vectors, and of course scalars, but mainly vectors, because in this case the differentiation involves an operator which you know about. This is the grad operator, or the del operator, or some people call it the nabla, but I'll be referring to it as the gradient operator. And in Cartesian coordinates, the gradient operator looks like this. These are partial derivatives with respect to x, y, and z in 3 dimensions. And so when you want to take the derivative of field, the gradient operator usually acts on a scalar, and it gives you back a vector, which is grad phi. The vector itself is gradient of phi, abbreviated as grad phi. And it looks like this. Partial derivatives with respect to x, partial derivatives with respect to y, and partial derivative with respect to z. And grad phi, gradient of phi is it has some very interesting properties that you can keep in mind. when you are actually trying to solve a problem in the exam. So the gradient of phi, how is it useful to us? So let's say, so there is the concept of something called directional derivative. When you're dealing with vector fields or scalar fields, the concept of directional derivative comes in handy. So what does it mean? Let's say we have phi, and we want to move in any direction s in space. We want to move in any direction s in space, and let's say this movement is from a point x0, y0, z0 to x, y, z, right? We want to move, and let's say that the distance is s, and so you know that this equation of line can be written in the parametric form: x0 plus as equals to y0 plus bs, and z equals to z0 cs. This is the parametric equation of the line, with s as the parameter. Okay, and let's say that I actually want the directional derivative, which is given by d phi of ds. d phi of ds. Okay, so how do I calculate the directional derivative when the x, y, and z are given in parameter form? Well, it's not difficult. It's actually it's how we go about it. So phi is a function of x, y, z, and this we apply chain rule. Del phi of del x, and we apply dx ds, del phi of del x and dx of ds, then followed by del phi of del y dy ds plus del phi of del z dz over ds. Alright? And what is the dx of ds? x0 is constant, so it's a, and y0 is constant, so it's b, and z0 is also a constant, so this derivative is a c. Now, all I need is to define a unit vector, which has a unit vector from x0, y0, z0 to x, y, z. And this is the unit vector. So now, as you see, d phi ds can be written as a dot product of gradient of phi dot u. And this is essentially the directional derivative. And you see, the directional derivative is given by the dot product of gradient of phi with the unit vector along the direction. So if you want the derivative along a particular direction, all you do is basically calculate gradient of phi and just take the dot product with the unit vector along that direction. And of course, you know that there's another concept which is extremely important in terms of gradient of phi for vectors. Is that let's take a surface of phi equals to constant. Okay? Let's say I take a tangent vector over here, a tangent vector at P, the tangent vector at P, and let's say I take three kinds of chords, point A, point B, point C, and I'm trying to, for each cases, I'm trying to find del phi over delta S. Okay? And you see, phi is fixed on the surface, so no matter wherever I travel on the surface, whether I travel at B, whether I travel at A, whether I travel at C, delta phi is 0. And so, if I take the limit of delta S tending to 0, delta phi over delta S, basically becomes d phi ds, and d phi ds is the tangent vector. D phi ds is the tangent vector, which is also 0. What does that tell me? What does that actually tell me? It tells me the gradient of phi, which is d phi of ds, gradient of phi of u, where u is the tangent vector. U is the tangent vector, is 0, which means the gradient of phi is perpendicular to u, but u is the tangent vector. So the gradient of phi has to be the normal. It has to be the normal at that point, at p. So gradient of phi is the normal at p, which gives us a very, very important result. So gradient of phi is perpendicular to the surface phi equals to constant. Always keep this in mind, so that whenever you are given an equation of any surface, all you need to do to find the normal vector to the surface at any point is to find grad phi, find the gradient of phi, and then just set in the values of x, y, and z for gradient of phi, and you get the normal in that direction. That's about it. That's it for this video lecture. Thank you for watching, and have a good day.